today I will present this framework, which now I rename it to ReMoRa, and it presents a resilient modular robotic application framework. The presentation you will feel is a little bit similar to Intrinsic, but we are the research project. So the motivation here is we got the industrial partner and they have certain requirements. And the first is they want to do this high mix, low volume production, so which means they need to switch to different automation system, like reconfigure the hardware, reconfigure the application, really flexible and fast, and still ensure the quality of the application. And they want to reduce the downtime and easily for the system to adapt to the failure. Yeah, here I found this nice picture about this reconfigured robot cell to present this kind of requirement. And the challenge now is first, if you want to overcome the flexibility, then it always requires the manual code because they're still using the PLC code. And it has limits the reusability of the software. And the integration is another challenge because for this kind of device, it usually has the tight coupling between the hardware and the software, and hard to adapt to the other different vendor. And the resilience is we want the machine still can continue performance even the failures happen. And transparency is we want to also have the runtime monitoring to see the system, what's happening, the log, behind the machine. And for my personal experience is I need to do quite some demo with the hardware, and every time I need to reprogram it, but I'm a lazy person, so I want to find a solution which I can really easily, fast adapt to any kind of application. So that's why we developed this framework. And in this framework, it has a 3 layer. So for current version, it's still based on the ROS-II ecosystem. And to be able to reuse this existing open source software, what we do is to create this skill server, which is kind of the wrapper to wrap this components. And then on the top, as user, when you create application, you don't want to do C++ coding. You want to just create your control flow, sequence, logic. And in that case, we are using the behavior tree, CPP. I think the developer is also here today. And between these 2 layers, we had this ReMoRa crawl layer. So basically, we had abstract the skills and also manage the skills at the runtime, and then also execute this control flow. So this is a more detailed design principle behind this framework. Basically, we have this skill chain, which has a skill server provide the service to the client, and the client you can use by the control flow. And in between, they have this interface. And we also have a quality guard, which we want to monitoring the service provider skill and to decide when should stop if something happened. So to use it, for now, we have this also packaged quite some skills and put in the skill library, which then you can use the GROOT, which also from the behavior trees, and to compose this logic you want. And then we also do the Docker containers, so package the software, which is easy for the deployment. And then we also create this Ravis plugin, so you can load the behavior tree you created in the Ravis, and then you can execute it with your hardware or the simulation. So this is an example how, from the system level, what is the difference between the traditional robotic system and our system. So in traditional way, you will have the move it or software or the component start, and you use a move group as the interface to control your manipulator. And in our case, is we wrap the move it CPP, the lower level, and then we create this skill wrapper on the top of them. And you can do the configuration to adapt it for the different type of robot or the planner you want to choose. And for this execute trajectory, we also have monitoring, continuous monitoring the collision. Yeah, so that's the more concrete example. For example, we want to use the UR5E and to do this pick place. And based on the skill chain side is all the skills which are available. And then you can do the parameterization and the composition. And then you can create the behavior tree. And yeah, you can also decide if you want to have a sub-behavior tree or the overall one's behavior tree. Yes, so here's the demo. And we have tried quite a different type of robot, but for the use case, we usually do is pick place. And from this side, you can see we also have created a skill which do the object detection. One is based on the Yolo-based. So basically, our student trained the algorithm and to train this model to detect this legal block. And then, yeah, you can wrap it as the skill and use it. And then there's also another one is use this Aruco marker, which is an open source package. And we just on the top of it wrap the skill, and it can detect this Aruco marker on the top of it. For the control the manipulator, it's still same behavior tree. And in this and this, between this, the difference is we basically change the planner. So in this case, we are using the pelts, and in this, we are using the OMPL planner. So you can see the motion or trajectory generated between different. This is this one is more smooth, and this one sometimes do this weird movement. And yeah, we also try using the same behavior tree logic to control the different robot just by changing certain parameters. Yes. So this is more like research work, and then we also try to integrate with some industrial device. So we got to the industrial project, and basically the pain of them is they usually do the PLC programming for their machine, but it's quite hard for them to find the new generation to do the PLC programming, and they usually like to do the modern programming like C++, Python. Yeah, so that's why they look into the ROS-2. And in this case, yeah, so in this case, we had to integrate control X and to control this two cylinder. And then we have another IPC to run the robot driver and our framework. And in this case, we also, for the control X side, we created the ROS-2 driver control inside of the control X. And for this motion, so you can see the robot is doing this disassemble this thing to put the thing in this reel. And in this case, we are not using the move it, and we are using the PyTask, which is also developed by the IPA, another group, and there's a link below. So basically it's using this force control to do the thing inserting and removing. Yes, so this year we also try some other work because, as you see, we still manually create a behavior tree, and we are thinking about, okay, why we don't try using large language model to do it. Basically the idea is, we can show the video later. So it's user give the natural language input, and basically the LM will generate the behavior tree skeleton. And by using this hierarchical scale atom scale chain and to compose this skeleton. But this is, another important thing for behavior tree to be executed successfully is the parameters. And to do so, we also don't want to manually put it. So we are using this MCTS, Monte Carlo chain search, to do the offline parameter optimization in the simulation. And then once we had the behavior tree ready, parameter ready, then we deploy to the hardware. I can show the video. Yes, so this video just shows this prototype, how we do it. yeah, we basically user group gives the natural input, which want to pick up the Aruco marker with the 42 ID number, and then place at this fixed position. And then we use generate the behavior tree skeleton. And then for this Monte Carlo tree search, the first thing is you also need the initial prior for each parameters. And we also use LLM to do some propose, which is a reasonable parameter. And then we do the offline training in the simulation. In this case, we are using the gazebo. And you can see this parameter will adapt during the time. And then we'll get many sites of the parameter with a different score, and then we choose I can choose top 3 in this case, and then redeploy in the simulation again to see, okay, it actually performs well. Then after we evaluate it again, then it will be deployed to the real hardware. But there's still has a thing to real gap. In our case, we know there's a gap between this how we control the gripper, how much to open and close, and in this we have to adapt it. And then afterwards we deploy it. So during this training, it can select the pelts planner over the OMPL. Yeah. And basically, we show is we basically run this behavior tree 12 times. And I think this was like one failure because this Aruco marker has accuracy issues. I can't find a really good position to pick. And also maybe the way how I glue the Aruco marker is not so accurate. Yeah, then I think we also try to deploy the third best behavior tree. So it's choosing the OMPO, but it also selects the path constraints to limit the joint movement. And in this case, it will be less this weird movement compared to you don't do the path constraints. Yeah, but it's still not so reliable as using pelts planner. And then we also try to use the same principle with the UR5E, but in this case, we just do the simulation. Yes, so this is about how we create normal operation. And another thing is we want to have this fault containment to make sure the application has awareness and to adapt to failure. So in this case, in our design, we had this quality guard. For now, for example, we can think about execution time. So you usually know how when execution time for one skills, and then when it exceeds, so it will decide to stop this service, and this control flow, this logic will basically also stopped. And basically, it can provide us two kind of information. First is at the system level. So basically, we know which kind of skill has a problem. And based on the skill chain, you can also trace back maybe which software components has a problem. Another part is we also have this application level awareness. Basically, we also create an extra package to monitoring the behavior tree execution to find out which node has issue when it's stopped. Then it's basically which leads to our current work is we are building this external recovery system. So we want to do is after we got this failure signal, we want to trigger this external system to basically to decide how to recovery and do the planning, or either need to create a new behavior tree to adapt the current one, or create the new recovery plan basically to skip from this failure and continue still make sure the robot reach the mission. Yeah, and we also think about what is the other potential work we can do. So for example, this predictive maintenance, which is also important for us. So basically, we are trying to build more rich data logging, because for doing some training AI model, you need a lot of data, and which is good data, has the best way is already labeled data. And yeah, if we can have this predictive maintenance model ready, and for example, for each skill, we don't need to wait the quality guard decided as error, but we can already stop earlier, and maybe don't need to interrupt the entire control flow execution, which maybe we can trigger the early to automatically adapt. And yeah, that's the one of our idea. And then now we go back to the summary. So yeah, so for our framework, we want to not just build the framework, which is easily for user has no experience to build application. We also want to have the reliability, resilience on the top of this framework. And for now, it provides this modular reusable framework for building the robot application by using this skills concept. And yeah, because we were using the behavior tree, and I think it make sure has at least it's transparent. And based on this design principle, we also we had this fault containment to at least trigger the stop before the failure happened. Yeah, so, and for now, this framework, which can provide this system and application level awareness, which can be the potential for the future work. For example, yeah, as I mentioned before, we are currently working on this external recovery engine, and predictive maintenance is our next step. And actually, it's also possible if we can also do the root cause analysis instead of just adapt the failure of this fault and continue the application. Maybe it will, if you do this again, this same failure will happen again. So the better is to find out what actually is the root cause. And yeah, and based on this data collection logging, we can also train the model, which can basically adapt the parameters during the execution. And our also next plan is to try this VLA, so visual language action, as a skill, because we don't really trust to use this VLA as a black box to do the entire application, because it's a black box. But VLA, I think, has the advantage to do some really fine actions. So we want to try just package it as one skill inside of this behavior tree. Oh, yeah. Thank you. Thank you for your attention. And welcome to the question.
So thanks a lot for the talk. And we have quite some time for questions. So please.
Hello. Thank you for a great presentation. My question is concerning some of these demos you had on the presentations. You mentioned sometimes that for some demos you used Move It, and for some you just mentioned some planners that you used. So I'm wondering, like, what are you using for managing the scene of the robot, like the cell limits, the collisions, the object themselves? How do you handle that?
Yeah, that's a good question. So for using Move It, I think we also have in the executing the trajectory, we integrated this planning scene, which actually used by the Move It. And when we switch to the new planner to do these things, actually it's limited by the collision check, because they are not using the planning scene, and we should have maybe like extra skill at the same time to parallel running to continuously check the collision. Yeah.
Thank you for the great talk. I have a question regarding this exact slide, how you were integrating the task of the PLC into your behavior tree.
Yeah, so actually what we do is we have tried, this is the example we are using the control X, basically has provided this data layer, and we created the ROS-2 control on the top of it, basically provide the interface to us. So we can send a command from the behavior tree to say, okay, I want to move the cylinder now. But it's basically the same as how you use control the robot to plan from A to B. And for that is just we provide a skill which can utilize the PLC device. And we also try is to use the Omron PLC. And I think we also did with OPC UA bridge by using bridge and bridge to the ROS. And now we also tried this to using the EtherCAT. Basically, we directly from EtherCAT to ROS to control.